Okay, I'm back and we're still talking about general properties of waves. And in our previous segment, we were talking about the different types of waves. And now we want to concentrate mainly on light waves. But since you're more familiar maybe with sound, I'm going to compare the two. So I'm going to compare properties of light with properties of sound so that you can see how they're alike. But remember that we're mainly going to be interested in light waves when we talk about stars. So the first thing I want you to know about is the amplitude of a wave. The amplitude of a wave is going to be the height of the wave. And you'll notice how it's measured. It's not measured from the trough of the wave to the crest of the wave. So a wave has a crest, and then it's got a trough, and then it goes back up again. So it's not from the crest to the trough. It's measured from the crest to halfway in between. So we're going to call that the amplitude. And for light, amplitude is going to be related to brightness. So the brighter a light bulb is, the greater its amplitude is going to be. If we're talking about sound, then the amplitude is related to the loudness of the sound. Okay, another property is called frequency. Now, frequency, in some textbooks, they use the letter F to stand for frequency. But in most physics textbooks, they use a different letter to stand for frequency, because the letter F is also used for focus of a lens, and we're going to learn about that later. But this is the letter that physics people kind of like to use. And I know it looks like a V, but it's not. So it's a Greek letter, kind of like a V, and it's pronounced nu. So this thing is nu. And then if I make a regular V, so if I make my V like that, and I know you're saying, but that's the same thing. Oh, it's not. It's not. This one looks like a bird, okay? But this one here is my regular V, and then that's going to stand for velocity. And we introduced that in the previous lessons. So frequency, and I'm going to try to use this letter to represent frequency, is going to be how often a wave repeats itself, and its official metric unit is going to be called the hertz, and then it's abbreviated Hz. So different kinds of light have different frequencies. So I'm going to put up here at the top the electromagnetic spectrum. So I'm going to use the letter R to stand for radio, and then next to that I'm going to put infrared, and then next to that I'm going to put visible, and then next to that I'm going to put the ultraviolet, and then next to it my X-rays, and then next to that, this is my symbol for gamma. So that's called gamma, and it's a gamma ray. So this is the electromagnetic spectrum. And now the frequencies are arranged so that this has a small frequency over here. And on this side, with the gammas, I'm going to illustrate it by having a large frequency. So in the electromagnetic spectrum, radio waves have the smallest, and then infrared gets a little bit bigger, and this gets a little bit bigger, and then finally over here, the gammas have the largest. So if on an exam, for all of my students who are watching this, if on an exam I said, which one has a larger frequency, infrared or ultraviolet, you would say the ultraviolet. So compared to infrared, ultraviolet would have the larger frequency. So every part of the electromagnetic spectrum has a different frequency. Now sound is the same way. So you can have different kinds of frequencies in sound, and then that's related to its pitch. So you can have low frequencies, and you can have high frequencies up here. So the higher the frequency, the higher the pitch. Well, we're not really interested in that. We're talking about astronomy. But I thought it is kind of interesting that there are different kinds of animals that can hear into the higher frequencies. So like, for example, a bat can hear frequencies higher than a human. And an elephant, on the other hand, can hear frequencies that are lower than what a human can hear. I wonder if the same thing is true for light. Are there any kinds of organisms that can see into the infrared part of the spectrum? And the answer is yes. Can you think of them? Rattlesnakes. Okay, so snakes that live in the desert have these pits on the sides of their nose that can detect infrared radiation, so at night they can see things like rats and rabbits that they want to be able to kill. Is there anything that can see into the ultraviolet part of the spectrum? Yes. And those are things like honeybees, for example. Certain kinds of insects can see into the ultraviolet because if you look at a flower in the ultraviolet part of the spectrum, it would have a different pattern to it. Look it up on the internet. And so that's how a bee can distinguish between different kinds of flowers, is because they can see a little bit into the ultraviolet part of the spectrum. Okay, let's go to our next one here. And so this just gives you a range of different electromagnetic waves, so you can see how small they are and then also how large they can be. Another property of a wave is going to be its wavelength. And so this time we're going to use a thing that looks like this. So that is, okay, that thing there. So that's called lambda. So it's a Greek letter L. So L for length. So it's the wavelength. It's measured in meters because it is a length. And it's the distance a wave travels before it repeats itself. So your typical wave, okay, so let's make a wave here, is like that. And so do you see that it repeats itself over here? So it starts here, let's say, and it ends over here, so that's where it repeats itself. So the distance between those 2 points, that's going to be the wavelength. And so the first picture there shows you how we would measure the wavelength for light. Now at this point, you shouldn't really understand that picture, other than the fact you see it's wavy. So light is a wave. And so the distance between one of the peaks to the other peak is going to be the wavelength. Now later, we'll talk more about that and explain what do we really mean when we show that picture there. And then the one over next to it is a sound wave, and you can see that the sound wave is pushing on the air so that the air gets more dense in some places and then it gets more spread out. And so again, you can measure the distance from one of those dense areas to another dense area, and that would be the wavelength of a sound wave. So in our next segment, we're going to talk about yet another property of a wave, which is going to be its speed. So I'll see you in the next segment.